In today's video, let us discuss about curve fitting to a scatter diagram using method of least square. What do you mean by a scatter diagram? Let us have a bivariate data. Obviously, we choose only the positive quadrant and we have a tabular representation of xi along with yi. Okay. We may represent this data as y depending on x or x may depend on y, vice versa. At this point, we just mean that this is a set of points xi, yi, I running from 0 to n. So there are n plus 1 points, and we would like to fix a curve. It may be a straight line, it may be a parabola, so that the data is represented by that curve. So obviously, we must choose a method of finding the suitable curve which best fit the given data set. That is the challenge. Okay. So I repeat, we would like to discuss in this video the method of least square. This is very important. To fit a curve to a scatter diagram or to a given set of bivariate values, tabular set of values, one depending on the other or vice versa. Clear? Now, just look at this diagram. Let us take that we are going to fit a straight line to this straight line to this data. So this is say x1 y1 and the first, or rather x0 y0 as we have shown in this table, to be represented by this point P0 in this diagram. And let us choose that this one is xn and yn. So all these other values are x1 y1, x2 y2 and xn minus 1 yn minus 1. We may represent these as xn minus 1 and yn minus 1, just the value previous to the last one. Okay. And if this straight line is represented by y equal to alpha x plus beta, where this alpha and beta fix up the nature of the straight line, we would like to minimize the error between the points on this straight line and the point given by the tabular values. What does it mean? Just see that if you put xn in place of x here, we get y equal to alpha xn plus beta, isn't it so? But according to this representation, this is not our yn. Our yn is this. So according to this fitted curve, the value is this, and according to the given data, the value is this. So this is the error, isn't it so? And we would like to minimize this error. So what we would like to do is that we put I here, give a summation here, I running from 0 to n, and put a square, so that S measuring the error involved in fitting the straight line to this tabular data may be represented by this. Now the question arises that why we take the square and then take the summation and then take the square root. For obvious reason, from this figure we can see that according to the tabular value, yn is less than the fitted value alpha xn plus beta, isn't it so? If we fit xn here, we get yn as alpha xn plus beta, which is, this is xn. So correspondingly the point on the straight line will be here. So this is y according to the straight line fitted to this data, but actual yn is this. So this is the error, which is obviously when we subtract the value according to the fitted line and the value in the table, we get lesser value, isn't it so? The tabular value is less than the fitted value. And in contrast, if we take this to be xn minus 1, yn minus 1 point according to the table, and we fit xn minus 1 here and get the straight line value here, so the straight line value is less than the tabular value or the value in the table. So the error is positive. So the cancels out when we get the summation. To ward off that effect, we square it, the difference, and then sum it, and then take the square root. This is easily understandable, isn't it so? Let us move on to take another look to that diagram. So I think we are into the understanding that what we intend to do, we have a tabular value given by varied data, and say we have exactly n number of values, okay, and we represent this as, we spotted this as scatter diagram. And now we would like to fit a straight line like this to this data. We are concerned in the positive quadrant only because these are all positive values, and we would like to fit this data to a straight line. Fitting a straight line to a scatter diagram, okay, which represents a tabular value. So if we assume that the straight line has equation y equal to alpha x plus beta, where you know that this alpha and beta are the parameter which fixes the nature of the straight line, and we would like to find out this alpha beta, or rather this straight line, which best fits this scatter diagram. So then we should try to minimize the error, which is represented as summation yi minus alpha xi minus beta whole square and square root over it. I going from 1 to n. Why? Because whenever I take, let us take the point of x1 y1 and x2 y, sorry, this should be y2, x2 y2 only, and let us take that this is x1 and this is y1 representing the point, first point p1 in the table, and let us take this to be x2 and y2 according to the table plotted in the scatter diagram. So according to the straight line, if we put x1 here, we get y to be here, alpha x1 plus beta will be here. So this is the error. And according to the x2, the y will be alpha x2 plus beta and it will be here. So here the error is this much and here the error is this much. One is positive and one is negative. In the first point, according to the tabular value, we have y1 lesser than the value of y1 fitted according to the straight line. While in the second value, we have the value according to the table to be higher than the value fitted in the straight line. So we take the differences and get the square, sum it up and take the square root. So this is the measurement of the error which we would like to minimize so that the best fitted straight line is obtained. Best fitted straight line is obtained, and this characteristic of the straight line, best fitted straight line, is determined by alpha and beta. And for that, we would like to employ the partial derivative method, which will minimize this quantity. Okay, we all know that since the error depends on this error, which is nothing but summation yi minus alpha xi minus beta whole square. See, this yi xi are tabular values, so they are constant. And for finding the best fitted straight line, which we would like to determine, is alpha and beta, which fixes the straight line. Okay, I think this is understandable. So we would like to differentiate this s with respect to alpha and with respect to beta, and we will make them 0 so as to find the extreme value of this function, for which we must have a maxima or minima. Okay, and for here we will find the minimum value only if we differentiate it with respect to alpha and beta partially. Since s is considered here as a function of alpha and beta, both xi yi are constant, so when you take the derivative of this, it turns out to be half s to the power, s is this, so we have actually half root over yi minus alpha xi minus beta whole square, and here we have 2 yi minus alpha xi minus beta into derivative of this with respect to alpha gives us minus xi. Okay, I think this is clear, because the whole, we should keep this symbol here and the symbol here also. Why? Because this is something root over capital X. So the derivative of root over capital X with respect to alpha is half x to the power half minus 1. So half x to the power minus half, which we have written. And then we take the derivative of x with respect to alpha, and when you take the derivative of x with respect to alpha, it becomes 2 yi minus alpha xi minus beta, and then chain rule derivative of this with respect to alpha gives us minus xi. And here we have the same thing, half summation 2 yi minus alpha xi minus beta by, here I have erroneously written the summation outside the root, which should be inside the root, this. Okay, and these two actually turns out to be summation, we cancel these two and it is yi minus alpha xi minus beta into xi equal to 0, and this gives us summation yi minus alpha xi minus beta equal to 0, because these two again cancels out and this 0 is in the denominator. So we should equate the numerator only to 0, and from these two we get let us take this first. So summation yi minus alpha summation xi minus summation beta is equal to 0, and you should remember that I runs from 1 to n in all cases. Okay, so obviously when we sum up beta from I equal to 1 to n, we have actually beta plus alpha x bar equal to y bar. Since this becomes n beta, and since we transpose them, it becomes like this, and then we divide n and replace 1 by n summation yi as y bar and 1 by n summation xi as x bar. So this is number 1 formula which you get from this equation, and now from the other equation, which is this, we get summation yi xi, we multiply them, is equal to, we can transpose them to the other side, right hand side, and it becomes alpha xi square and plus beta xi. And we deliberately divide both sides with n just to make it x bar, and we have 1 by n summation yi xi equal to alpha into 1 by n summation xi square plus beta x bar. This is term 2, and we can easily calculate alpha and beta from these two equations. Okay, whenever xi and yi are given in a tabular form, which I have shown xy, and we have corresponding values of xi yi like this. Okay, xn minus 1, yn minus 1, xn yn. We can easily calculate the product of them, the square of them, and add them up. and put the values here and find out alpha beta, which gives us the best fitted straight line to represent this data. Similarly, one can think of fitting a parabolic data or an exponent parabolic curve. Sorry, I should say parabolic curve represented by this. Okay, this is a parabolic curve. We can fit this parabolic curve also to that tabular data. We can as well fit algebraic curve a b to the power x. Actually, this can be reduced to this form, which is actually nothing but this is actually exponential curve. We have used capital Y in place of log y, and then we have the straight line. So you can fit this data also, this curve also, this curve also to a bivariate data, or this curve also. Now the question arises, what is the best fit? So for that matter, we will have to calculate the goodness of fit, and to measure the goodness of fit, we require some idea of probability.